Anyways, hi, hello, my name is Quentin Stout. I'm in the Computer Science and Electrical Engineering Department. We're on North Engine, or part of North Engineering campus. If you look, this is our new building, or relatively new. If you look right there, that's a piece of the ENIAC. Okay, so you can come to our building and find a little piece of the first general purpose electronic computer in the world. And if you go right there, you'll see that there's at least one professor who works late and actually is very dedicated and so on, or else I forgot to turn off the lights, one or the other. Okay, well, this is only 75 minutes, so it's going to be a very short overview of kind of what is parallel computing, why might you be interested in it, what are your options, and so on. So as I said, we're going to talk about what is it, why you would want to use it, and so on. How do you get access to resources? There's going to be another part at the end. And one of the things is, please feel free to ask questions as we go. It doesn't do any good to ask questions at the very end, because by then you've forgotten what the question was really all about anyways. And Maria will give us extra time if we go beyond that. She's supposed to time me and tell me to stop. And also, a little bit of this material appears in this tutorial, Parallel Computing 101, that I teach with Christiana Jablonowski. She's in AOSS. That tutorial we teach at a conference called Supercomputing, which is the major interdisciplinary conference in high-performance computing. Okay, so the big question is, why parallel computing? All right, and one of the biggest reasons is because of a couple of curves I'm going to show you. This is based on lots and lots of historical data, personal experience, and analyses by a whole bunch of people. What you want grows exponentially in time. Okay? So if you look at over time, what people want. Now, in terms of what you want in terms of resolution, what you want in terms of data, what you want in terms of science, and so on, keeps growing. So for example, maybe you're doing a climate model, and right now you've got let's say a 20-kilometer resolution. Well, in a couple of years, you really want a 10-kilometer resolution. And if that's just in horizontal coordinates, that means you need 4 times as much. And then a couple of years after that, then you start asking, well, can I have 5-kilometer resolution? So it's another factor of 4 in terms of complexity. One time I was at a NASA presentation a little while ago when they were describing that they had a very, very accurate model of airflow past a rocket. They also had a very accurate model of the engine and the exhaust coming out of the engine. It's very complex, it turns out. What they couldn't do, though, is because they didn't have enough computing power, is actually turn the engine on and have the rocket go through the atmosphere, okay, because the interaction was too complicated. Okay. And so that's the sort of thing I mean by complexity. Okay. And complexity is always going up. You can also think of complexity as a competitive advantage, that you can, say, do something that other people can't do, and so on. So this is what you want. Okay, now there's a minor problem. This is what you get. And in fact, one of the chip designers now just came in, so you can talk to him about why you can't actually do this. Okay, anyways, so the problem is, you've got this curve here, but it turns out this is what you're actually getting now. Okay, so if you go back several years, it turned out every year and a half or 2 years, the processor speed was doubling. And if you're old enough, you remember when Intel used to market about, oh, our computers are now at 6 megahertz, and a couple years ago it was 3 megahertz, and so on. You may have noticed that Intel doesn't market like that anymore, because in fact they're not getting any faster. Basically, the computer you can buy now is roughly as fast as it was 3 years ago, 4 years ago. They're not speeding up. Okay, well, this gives you a fundamental mismatch. You're here, expectations are still going up exponentially, okay, but you're here. Things have flattened out. There's only one way you're going to get that performance. There's only one way you're going to solve that. Okay, if you need to do that much computing and the computers aren't getting any faster, you better start using a bunch of them together. Okay, you're kind of forced into that, and you're going to be forced into it more and more and more. As your expectations continue rising and the computers aren't getting faster, you're going to have to go to parallel. Now, there's another thing that comes in here, sorry, that's actually pretty useful for you, is there's another thing that chips are giving you. Okay? The other thing that chips are giving you is more and more transistors. And this curve is continuing to go up can't get a very good angle here. This curve is continuing to go up at an exponential scale. That every year and a half or 2 years, you're getting twice as many transistors. That curve is projected to continue out for, say, 10 years, roughly. It gets a little, if you go into out years, it's less certain about it. Okay, so you're getting more and more transistors on that chip, okay, but the processing isn't getting any faster. And there's a bunch of tricks people are trying to use in the architects to try to get it to go faster, giving it more cache and a whole bunch of things, branch prediction, and they're kind of running out of tricks, okay? So now what's started to happen is, all right, we've got a gap between we're getting more and more transistors, the things we can build aren't getting any better, aren't getting any faster. So what we're going to do is then say, okay, we're going to give you a bunch of them. Sorry. Hello. Sorry about that. We're going to give you a bunch of these processors. They're all going to be running about the same speed, but we got more and more chips. We're just going to replicate them. So in other words, another reason to go parallel. Okay, another reason to go parallel is everything you buy is parallel. In fact, even if you buy an iPhone 4S, it's now got a dual processor. Okay, so now I'm going to talk a little bit about parallelism, and again, as I go through, I'll try to show you a couple examples, just a little bit to give you a small bit about the flavor of parallelization. Not all parallelism is the same. So there is stuff called embarrassingly parallel. That's a technical term, okay? And basically what happens in embarrassingly parallel computing is you've got lots of independent tasks, okay? And you need to get them done. For example, if you're doing simulations, sometimes people do things called parameter sweeps. They say, well, I'm going to simulate this fuel injection system with this fuel pressure, then I'll simulate it with this other fuel pressure and another fuel pressure, and I'll change several other parameters and so on. Well, those simulations are all independent. Okay? So one thing I can do with my parallel computer, my multiple cores on my chip, or a bigger parallel computer is just say, well, run all those simultaneously. That's parallelism. It's a very easy parallelism. Okay? And the thing is, if you look at the CAC, at least the last time I looked at it, a lot of the usage there is actually this form of parallelization. So you may get people that are using, say, 100 cores, but it turns out if you look at it, they're using maybe 100 different programs, or maybe they're using like 10 concurrently, each of which is only using 10 cores. So it's small parallelization within the problem, but then they're running many instances of it. Now, the thing is, if this is what you can do, this is what you should do. This is exactly the correct way to do the problem. And we'll see that a little bit later. If you have to run many instances of the same thing, varying parameters or different data sets, if it's data intensive, if you can do it this way, by saying run a bunch of them not connected to each other, that is the most efficient way to use a computer. Okay? It's boring from my standpoint, but it's the most efficient way for you to get your analysis done. Now, what I'm most interested in is the things that aren't that easy. If everything was like that, you wouldn't need computer scientists to do parallel computing. So I'm more interested in problems that are more tightly coupled, where you have to actually work hard to get on the problem. You've got one problem, and you're now trying to use many processors. So for example, one of the early ones we did was a car crash for Ford Motor. That helped start the CAC. Okay, they've got one car crashing right now. Or you've got one climate, model the climate. You may need a supercomputer to model it accurately, but all the processors are working together on one problem. So in that case, it's no longer embarrassingly parallel. I have to use that whole parallel machine to do that one problem. So that's what I'm most interested in, and presumably some of you are interested in as well. Now, the thing is, in many cases, you need new approaches. And I'll talk about that a little bit more, but it turns out a lot of what you do maybe initially you've got some way of doing it right now, and then you look at that doesn't work very well in the parallel machine. So often parallel computing has been forcing people to rethink some of the ways that they're solving the problems. And another thing is, this is a really important point that gets overlooked sometimes, is that algorithmic advances have been as important as hardware advances. Okay, I remember going to one of NASA's presentations, and this really good presentation about the advances in linear algebra solvers versus the advances in computing power, going back to the ENIAC. And it turned out that they had about the same slopes on that exponential scale. Okay, so you put both together. In fact, using the parallel computer without the advances isn't going to get you anywhere. And there was a recent National Academy of Sciences report that ended up pointing out the same thing, that algorithms are important as well. However, they're not as great. You know, you can't have the top 500 list of the best algorithms. There's a top 500 list of the fastest computers. It's a worthless list, but anyways, it's politically very useful to have it and so on. So algorithms aren't as sexy as the hardware sometimes, but they're critical. Okay, so as I said, one of the things that helped start the CAC was a car crash simulation that we did long ago now, 20 years ago now, I guess, for Ford Motor. And there were a bunch of computer scientists and some mechanical engineers and so on working on this. And basically what you have is you're going to simulate the car crashing into something. Okay, and a typical way of doing a simulation like this is you have to somehow or other model the car, and a typical sort of thing is I end up, say, triangulating it. Actually, they were mainly looking at the surface of it because they didn't have enough computing power to do it as a true 3D. And so I break the surface up into, say, a bunch of triangles or rectangles or whatever, and that represents the car. One interesting thing about this was they wouldn't tell us what the car was. It was a secret what the car was, which is kind of amazing because it looked a lot like a Mustang. Okay? But anyway, this doesn't. But, anyway, so you just model the car this way. You break it up. And then a typical sort of simulation thing is you end up wanting to simulate what happens in tiny time steps. So what happens in the first microsecond, what happens in the second microsecond, third microsecond, and so on, as the thing is crashing. And so at each time step, it turns out if I look at one of these little triangles down there, what it's going to do depends on, well, like what sort of momentum does it have, what sort of energy does it have, and it only depends on the things adjacent to it, okay, that they are the ones that are pushing on it and so on and constraining it. So its stresses and strains are given just by in that next microsecond, are given just by the things that are adjacent to it. Okay. So the whole simulation consists of basically, it basically consists of, I'm going to go through a bunch of time steps, however long my simulation is. And then what I'm going to do is for each of those little finite elements, those little rectangles or triangles and so on that I have, what I want to do is I want to go through all of them here. So I go 1 to the number of elements I've got. Then what I'm going to do is just update it. What's its new status? Does it, where is it? Is it starting to bend, for example, if it's metal? What is momentum, kinetic energy, and so on? I want to get its next status in that next time step. And as I'd already mentioned, the way I get that is I have information about it, what is it right now, and about its neighbors, where are they right now, and that will tell me where this one element goes in the next time step. And then I do it again for all the time steps, so everything just moves along. Okay, so that's a classic sort of simulation. It comes up in many, many different types of things, climate modeling and so on. Okay, well now let's do it in parallel. Okay. So what I'm going to do right now is just use a standard parallel computer. Like you can go to CAC, they have their computer called Flux. If you just go and use Flux, you could think of it logically as pretty much like just a bunch of boards, like from your laptop or whatever, just put together in a cabinet with an interconnection between them, okay, that links them all together. It's more sophisticated than that and so on, but that's basically what it is. It's called a cluster computer, and that's a standard sort of thing that people use. Okay, now, when you've got that board, okay, then multiple boards, then you're going to have the situation that, well, I've got information here and I need to send it somewhere else. That's going to be called, they're going to communicate via messages, sometimes called a message passing system. Okay, so the processors communicate just by messages, just similar like your laptops are communicating, wirelessly with other servers and so on, or if you're using an Ethernet, the same thing's going on in that backbone Ethernet. Now, suppose I got like 1,000 processors. I don't want to write 1,000 programs. Okay? So the way you do almost all parallel computing is you write one program. That one program is then used by all the processors. Okay? That's called SPMD, single program multiple data. That's the standard way of doing things. Sometimes there may be like two programs. You may have like one program which is doing, say, all the simulation here. You may have a separate program that's actually doing, say, visualization. And you may be sending data from the one block of processors to another block of processors doing that. But that would always be a very small number of programs. Okay, so typically you think of it as a single program that all the processors are running concurrently. So for example, here's what it would look like. Okay, in this case, what I did is I've got a very low budget. I've got 3 processors. Okay, so I've got 3 processors, and what I do is called domain decomposition. I break up the car into pieces. Okay, and you could ask, how do I decide the pieces and so on? It turns out there's a whole bunch of tools that do that. You actually learn techniques like that, like there's things called space filling curves or ham sandwich theorems and so on that do it. So there's techniques for doing that, and you have to learn the appropriate technique for your discipline. If you're doing something data-oriented, you'll have different techniques. If you're doing something graph-oriented like social networks, there's different techniques for doing that. So whatever your application is, there are probably techniques already for breaking it up into pieces, and that's called the domain. So you do domain decomposition. So now what I'm going to do is say, all right, I've decomposed it, and I've got a blue processor, a red processor, and a green processor, and I've assigned those elements. Each element gets assigned to one processor. That processor is going to be responsible for updating the status of all those elements. As the simulation is going through, it will keep those elements and just keep advancing them through time, just like I did in the serial computer. Okay, that's sometimes called owner computes. So one processor owns the element and it keeps computing its status. Okay, well, the parallel program is really simple. It just says, okay, here's what I've got going on at any processor. Remember, all the processors are running the same program. You'll see a little bit later, each processor has to know which one is it. Am I the red one, blue one, or green one? Okay. It'll be more clever like numbers, like 0, 1, 2. So it'll know which processor it is. And then so for each processor, it's going to go through and say, all right, I'm doing the same time steps that the original thing was going to do. And I've got some number of elements. I don't have them all, just the ones I have. And then again, I compute the status, the state of that element based on its current state and the state of all its neighbors. Okay, now, this is actually useful because if you already have code, let's say you've already got some simulation or something you're doing already, and now you say, I want to make a parallel version of it because I have bigger inputs, I want more resolution, again, whatever it is you want to do. One of the nice things about this is, notice that this compute the state, so on, that's the same code. It's exactly the same code. Whatever that code was you had before, it's bang, you put that is the same. The only part that's really parallel is this, that I'm only going through, that I've decomposed it, and I've got, oops, why does this not work? I've only got, again, a certain number of elements, a certain number of elements here in the processor, but pretty much the rest of the code is the same. Okay. And that's one of the things, by the way, you want to maximize. If you're going to do parallel computing, you'd like to maximize the amount of stuff you can use that's the same. Particular parallel programs are typically pretty big. Maybe you've already got 10,000 lines of code for what you're doing. You want to use as many of those 10,000 lines as possible, although you're not going to be able to use them all. Now, there is something hidden in here, though. So again, there's this obvious thing about, well, I only compute over the elements. Okay, and then the thing is, well, it's based on my current state, the previous state, and the state of its neighbors. But there's a problem. When I decomposed it, not everything had all its neighbors in the same processor. So again, you don't have them all, and so it turns out, well, look, what's going on is for example, the blue processor there, it shares a boundary with the red processor. Red actually shares with both blue and green. So what happens is, for the blue processor, I basically say, okay, it needs the data from the red processor about what are those neighbors of the things that the blue processor is responsible for. Remember, its owner computes. Blue processor is responsible for those blue triangles, but it has to get information from the red processor. And similarly, those things are called ghost cells. They're just copies. Okay? So the blue is not going to do any of the calculation of those dotted red things. It just will get a copy from the red processor saying, okay, here's what I calculated. Bang, just use that. Okay. So one of the things is, though, this now means I'm doing things that I wasn't doing in serial. I wasn't doing it in my normal processing. So I've got to be careful about this. And it does a couple things. What you don't want to do is you don't want to have the blue processor have to send a message to the red processor saying, hey, I need this information from you. Well, at least for this sort of application, it turns out it always wants the same information. And in fact, red could pre-compute what does blue need from me. Okay. So rather than send a message from blue to red saying, give me this information, and red then sending it back, it's a lot more efficient, cuts the round trip time in half by red just sending what blue needs. Okay. And similarly, blue is going to send information to red and so on. So one of the things you want to do in parallel computing is try to keep those messages down, because that's overhead. That's stuff you didn't have before. That's new computing, new computations, and you don't want to do much of that. You want to keep that part down. And it's called parallelization overhead, and actually the messages are one of the major issues there in terms of getting the parallelization overhead. There's another form of parallelization overhead that is also important. Namely, suppose I hadn't done a very good job of domain decomposition. Maybe I gave red too much to do. Well, then I'd be in the situation that the other problem I've got now is that red would be taking longer than blue and green, okay, but they can't get ahead of it, right? They constantly, each time step they need, well, what was red's previous calculation? So if I did not do a good domain decomposition, then I get this other overhead, namely I get the synchronization overhead that some things are just sitting idle, waiting for information. So suddenly there's a bunch of places where things can be happening in parallel that you don't want to be happening in parallel. Okay, well, it's kind of important then to understand kind of how do you want to measure this? Are you doing a good job? What is it you're trying to do? And so on. So suppose I pick a problem, A. So in this case, A was car crash. And I want to look at a couple things. I want to compare serial and parallel. So let's say I've got a good serial algorithm for it. Either I've generated it or it exists in the literature or whatever. So for the serial time, I want to know, as I solve a problem of size n, how long does that take? Now, this is kind of Kahneman computer science approach to it. I'm assuming right now, incorrectly for the car case, that the time only depends on how many finite elements there were. Okay, so I'm measuring time as a function of how big is the input. For the car, it's complicated because glass is a little bit different amount of time to compute than metal does, and so on. So it's got to be a little more sophisticated than that. But for many problems, basically, if I give you the size, that's going to affect the running time. If I give you a bigger matrix, you know how long it's going to take. It's going to grow as the cube. If it's n by n matrices, for example, it grows as n cubed if you do normal things. So let's say I abstractly at least have a measure of how long does something take as a function of how big was the input. Well, when I go to parallel, now there's two parameters. I could ask how long does parallel time take? So I've got my parallel program right now, and I'm trying to evaluate my parallel program as a function of how big is the input and how many processors am I using, P. And notice, by the way, that I'm emphasizing it's my program versus the original serial program, because maybe, in fact, as I'm developing, I'm going to develop several potentially different versions of this, and I'm trying to measure the current version versus what presumably is roughly static, the serial program that's out there. Well, then there's a few really important ideas. One that you'll see used a lot is called speed up. I just say, okay, what's my serial time divided by parallel time? Okay. So you want speed up to be big, right? Because you want parallel time to be small. So you want speed up to be big, and in fact, if you think about it, you'll probably want it to be p. Now, there's another measure, efficiency, and it's defined in terms of cost. So another way to think of things in terms of cost is I have my serial program. It's running for a certain amount of time. If I go to flux, I'm literally paying cost. You know, how long does that program run on a, say, one core, one processor? Okay? That's how long it takes, and I'm just paying that cost. Now, if I buy P processors, okay, then the total cost is I've got all P, and I'm paying for it for the time that they take. So the cost for the parallel is just P times however long it takes. So then efficiency is the ratio of the cost of the serial divided by the cost of the parallel. Okay? So you want efficiency to be 1. Okay. Actually, I prefer efficiency sometimes than speed up, just because it's a little easier to understand the curves. But either one is fine, and you can convert between them. Okay, so here's a situation that comes up a lot. Okay, so here I'm looking at number of processors. So this is P, and here I'm looking at speed up. Remember, speed up was the ratio of the serial time divided by the parallel time. Okay, so perfect would be this blue line here, which would mean as I put P processors on it, I get P-fold speed up. That's also known as linear speed up, okay, which is a little bizarre because it's only one line out of infinitely many, but somehow that one line they call linear speed up. But anyway, so it's perfect speed up. The green line represents what you commonly get, okay? Even if you're doing a pretty good job, you'll often find that your speed up looks like the situation in the green. Now we'll come back a little bit about why would it look like that. Sorry. And occasionally you're going to get the red. Okay. And if that seems weird to you, have you ever been to a committee where there's too many people? Okay, and you sometimes wish, like, could you stop talking? Okay. So in other words, one of the problems with having the parallel computing is you get these messages and so on. So one of the problems could be you actually are getting overwhelmed with messages. Messages are actually interfering with getting work done. Okay. And it's actually easy to end up with that sort of situation if you're not careful. Well, the green, really you can understand in terms of a thing called Amdahl's law. If you're old enough, and we're here long enough, we used to have Amdahl mainframes here long, long ago when we had mainframes. So it's the same Amdahl, Gene Amdahl. He used to be at IBM, and then he formed his own company. Well, when he was at IBM in 1967, he made this simple observation. Suppose I look at the running time. I've got some program, some input. Okay? And I look at that program and see as it's running, or look at it, I analyze its running time, and look at the code where that was generated, and you'll see that, well, some of that code is like, I don't see how in the world I could parallelize that. Okay? Whatever I do, that's going to be just as it is. Okay? Some fraction of the running time. Okay? And then there'll be some other part, and I say, okay, I can parallelize that. Okay, well, suppose you did that perfectly. Suppose you said, all right, that part I can't parallelize, that fraction f, and then all the rest, the 1 minus f, suppose I put P processors on it and I parallelize it perfectly. Okay, so the time for that would be the time that I had before times. So I get perfect parallelization on the part I can parallelize, and I'm stuck with parts I can't parallelize. And then that's for time, you work it out for speed up, and you end up getting, you just calculate it out, and you get speed up of that. And notice your speed up can never be more than 1 over f. Okay? Even if p goes to infinity. Well, here's the problem. Amdahl, they were at IBM, they had lots and lots of codes, they went around. Amdahl noticed that in many of these codes, sorry, F was about 10 to 20%. In other words, the speed up was at most like 5 to 10-fold. You look at this code, F is 10%. The best you can do if P goes to infinity is 10-fold speed up. Okay, so that was an obvious conclusion then. Parallel computers are not going to be very useful. Okay. This is actually important. It actually convinced some companies to just not really explore that. That is an option. Well, fortunately, he kind of overlooked some things. See, there was a minor chicken and egg problem, like with new approaches. Why would you have found codes that were easy to parallelize? There were no parallel computers. Why would anybody have been writing codes with the idea, I'm going to parallelize this in mind? Okay. So this chicken egg problem is actually quite complicated. It's complicated when people are looking forward to future architectures and things that they might add. Again, well, is that going to be useful for a lot of codes or not? And sometimes it's very difficult to tell that. And so since nobody tried to get that F small, that fraction small, maybe in fact there's new programs that can do much better on that. And in fact, we're always trying to do better on that. So one of the facts you're going to encounter is, let's say you can drive F down to, say, 1%. So that says, well, potentially you could get up to 100-fold speed up. So that's really nice if you're using up to 100 processors. Actually, it turns out if you have 100 processors and F is 1%, you actually only get about 50-fold speed up. So even by then you're curving out. Remember I said common is curving down like that? Okay, it's because you still work those curves and you realize, well, now it's not like I go perfect and then I hit the limit. It's like, nope, this is what's happening. And so it turns out, let's say you get it and you get, say F is 1%. It works fine for the size of problem you're doing, and then you start doing more and more and you say, well, I got a really big problem. Now I want to use, say, 1,000 processors. Well, again, 1,000 processors does you no good just if F is 1%. So now you have to work even harder and get F to be down to 0.1%. And so on. So one of the things is you're constantly trying to push F smaller and smaller and smaller. Okay. Now, as a computer scientist, that's great because that means there's an infinite sequence of theses about how to get F smaller and smaller. Okay. But in general, it gets harder and harder. Each time you've gotten it down to one number, then it gets even harder to get the next time small. Now, another thing that he didn't notice is the memory hierarchy, and this is actually an important reason for buying parallel computers for some applications. If you, like your laptop, if you have a relatively new laptop, you've got a maximum of 8 gigabytes of RAM on it. Well, suppose you have a problem for which you need 100 gigabytes of RAM. Well, the only way you're going to do that on your laptop or on a normal server would be you have to put most of the data out of disk. They're constantly swapping things in and out of disk. One of the things parallel computers give you is a lot of RAM. Right? If you have many copies of this, many boards, I have lots of RAM there. So actually it could be that I gain an advantage automatically because the parallel computer can use more of the faster memory. And another thing he didn't look at was scaling, about what fraction of the time is actually spent in the parallel, what amount of time is spent in the parallel sections. And here's really what's going on there. If you look at code, you'll find that there may be, even if it's a good parallel code, there's going to be some parts that you really can't parallelize very well. You've got to maybe initialize some things and so on. It turns out, okay, that's going to be serial. Then you may have, most code has loops in it. At least the code, you're looping over data, you're looping over the finite elements, you're looping over time. Okay, so you've got loops that are going on in the big code. And so you may have loops you may have a loop which is just a single loop, or like in the car example, there was an outer loop of time and an inner loop of over the elements, and so on. Well, those are the things you parallelize. So the things in red I can parallelize. The things in green say I can't parallelize. And now I ask, well, what happens if I give you a bigger input? Well, as I give you a bigger input, the part I can parallelize becomes a larger fraction of the total time. So as I get bigger and bigger problems, the parallelizable part becomes a bigger and bigger fraction of the time. That means F is going down, just running the same program. Okay. So what you do in that case is you say, you often link how many processors do I have to how big is the problem. Okay. So Amdahl fixed the problem, don't change it, and now add more processors. But it turns out the way many people do it is they say, I need a bigger problem, I need more processors. I link the two. That's called weak scaling. What Amdahl originally did was called strong scaling. And in fact, that's most of the things I know of are run in weak scaling. The climate models, the car crashes, and so on, it turns out we basically fill the memory of the number of processors we have. Okay, that's basically how we set the size of many of our problems. So that actually gets around then Amdahl's concern. So again, just kind of summarizing this, so what you need to do if you want an efficient parallel program is you're going to have to eliminate or greatly reduce those serial sections. Again, that's really what Amdahl's law is all about. And I've already mentioned this, that you've got to really concentrate on evenly dividing work. It does no good if I have 100 processors, 99 of them are very, very close to what the average work should be, and one of them is doing 10 times as much work as it should be doing. Okay? If I just screw up one, then it limits all the others. Okay, so one of the problems is the more processors I have, the more likely it is that, well, one of them is ending up getting, not getting its share. It's getting too much. It doesn't matter if some of them, by the way, are a little bit below. You care about the one which is most above. Okay? And that's always a problem. And again, as you get more and more processors, that becomes more and more difficult. And then, as I mentioned already, you're going to use domain decomposition typically. As I mentioned, it really depends a lot on what sort of problems you're doing. Databases, you end up, typically your domain is the entities that are in the database, so you divide up the entities, people or whatever it is, the data that you've got, you divide that up evenly. The car crash thing was used, again, these geometric constraints, and used things which actually use the geometry. It's sitting in 3 space, and the only communication was things that were adjacent to each other. So I say, okay, here's this geometric object, and there's techniques to do that. Again, social networks would have different sort of techniques for dividing it. So you have to learn in your discipline about what is it, the techniques that are used for domain decomposition. Notice that one of the things I didn't decompose was time. So I did that big simulation. Again, so I had a loop. The outer loop was time. The inner loop was going over all the elements. Okay, so if you look at simulations, for example, that's a classic sort of situation. It's very hard to parallelize time. Okay, I mean, you can read science fiction novels and so on. I mean, so it comes up in a lot of science fiction novels, but you don't parallelize time, okay, unfortunately, because you have to go through it. What you do parallelize is space. Okay? And the same thing happens like if you're modeling, say, ATM transactions. Okay, you can model lots of different accounts. That's kind of the equivalent of space. But on each account, you have to do it in serial. You can't, like, take things out before the deposits were put in. Okay, so many different applications have this thing things that look like space and things that look like time. And of course, the other thing is you don't want to introduce overhead. You don't want to add all this communication that wasn't there. And again, that's typically messages back and forth. Every once in a while, though, you may get messages that go between all of them. For example, one of the things that happens with the car is we had to make sure that you were preserving all the energy of the system. So at some point, you had to sum up values from all the different processors. Okay? Well, if you're summing up values from all the different processors, you have to have an efficient way then of combining that information. Things like that happen a lot, and fortunately, those are already built into all the systems you're going to use. Operations like that, it's called a reduction. There are efficient ways of doing it. You don't have to write that. But every once in a while, you do get a situation where everyone has to communicate with everyone else. Then you're in that situation like the committee. That's exactly what you don't want to do, because the communication can start then overwhelming the calculations, just because you're sending all those messages. Now, there's different types of parallel computers, so sorry, that it's kind of important to understand them because it's going to affect how you can use them. I actually described a distributed memory network. Okay? And again, this is also sometimes called a message passing network. So in a distributed memory system, I've got a network, something that connects it together. So you could think of wireless network, Ethernet, InfiniBand is actually the system that they use in here. Okay, in a distributed memory network, I've got processors, I've got memory, and then I've got, say, cache that each processor has some copy of part of the memory for more efficient computing. And this is pretty much like if I had an individual system. This would be really easy to put together. You could put it together in a closet, in your dorm room, whatever. Another option would be I've got a network that connects things together, and I've got, what's this thing not work now? That's what I get for taking something from a conference. Anyways, so what I've got there is I've got memory at the top, I've got a network, and I've got processors that can connect to it. So shared memory is nice in the sense of I don't have to worry so much which processor has it. It can be, I just worry about I have to know a memory address. I don't have to know a processor that has it. The distributed memory, the reason it's called message passing is, notice that one processor doesn't have a direct path to memory and another processor. Okay? It actually has to go over the network, and then it actually has to send a message, basically, to the other processor saying, I need this information. Or, as I already pointed out, it's better if the one that's got it knows who's going to need it and sends it out. So in the distributed memory system, the processor gets involved in the communication. And in the shared memory system, there's the processor needing the information is there, but it doesn't need any other processor to be involved. And actually, we've got examples of this here. So Flux, the thing at CAC, is a distributed memory system. Okay, it's basically, again, a bunch of boards, and if I want something on another board, a message has to go there, or somebody's got to process it. There's more sophisticated ways of processing it called DMA and remote memory access techniques and so on, but basically something at the other end is processing it. But actually we have shared memory. The Flux boards are shared memory systems. Just like your laptop is a shared memory system. Your laptop is, say, quad core or 2 cores. Okay? So you've got 2 cores on there, and there's RAM that they're sharing. Okay? And on the Flux systems, for example, it's a slightly bigger board, and what they have is 2 sockets, 2 places the chips go in, and the chips that they're using for the calculations there are more oriented towards doing intensive calculations rather than your laptop. And so they each have 6 cores on the socket. So if you use a single board, you can actually do 12 things going on simultaneously in a shared memory environment rather than you can get more cores, though. I forget how many they're up to 2,000, 5,000 cores in the whole system, but then if I have to teach the whole system as being a distributed memory. Okay. So actually one given system you've got has got these 2 different aspects to it. So I want to just show you a little bit about how the differences are about when you're writing for distributed memory or shared memory. Okay, so if I'm writing for distributed memory, okay, one of the things is I want programs that are going to run on many different computers and for many years. When there was only a mainframe or one computer, it's like, okay, I write in Fortran or I write in C++, and basically it's portable, and you've been able to do that for years. Okay, so that you're already used to that. Okay, well now I want to go to parallel computing, and actually if you go back, say 20 years ago when we got, say, the first parallel computers here, it was actually quite a problem because you would write for one computer and then you go to a different parallel computer, a different vendor, and you have to make a bunch of changes. Furthermore, there are some dramatically different architectures. I already showed you, like shared memory, distributed memory. Well, if you want to make it the most portable, okay, what you would end up doing is writing in a thing called MPI, Message Passing Interface. MPI works on essentially any distributed memory computer there is, except for some really exotic ones. It essentially works on any distributed memory computer. It works on any shared memory computer. So if you write an MPI, you can get it to run anywhere. Furthermore, MPI is a standard. It's been around for a decade. It will continue to be around for decades. So if you're spending a lot of time developing the parallel program, MPI is actually a very, very safe investment. And what you do with MPI is it's designed for Fortran or C, C++/C. What you end up doing is you've got your C or Fortran program, and then you insert MPI commands in there. So like MPI subroutine calls get inserted into the program. And there's versions for different, they're essentially equivalent for Fortran and C++. Another nice thing about MPI, by the way, is you can get it for free. In fact, if you've got an Apple laptop, you probably already have it if you on it. You just probably haven't been using it. But you can get it for free, and you can go on the web, you can get it for free. So this means things like if you're just building a little cluster computer in your home closet and putting it in there, you can then get the MPI on there for free. Okay, and at the end of the talk, I'll show you some resources, and it'll be listed there about how to get that. Well, here's a tiny, tiny example. All right, so suppose, this is incredibly trivial, but I can only fit so much on one page. Suppose I have a bunch of processors, and I want to sum up all the, everyone's got some sort of value. And I want to sum up all the values and have, I want to get the sum. And let's say in this case, I want processor 0 to get the sum. Okay, we're in computer science, everything starts at 0. Okay, so if I have P processors, they're 0 to P minus 1. Okay, and often you designate 0 as being special, so I want processor 0 to get the sum. All right, well, I'm writing this SPMD, single program, multiple data. Okay, so every processor is running the same program. Okay, but some processors are different than others. So if I'm processor 0, so in this case, if my rank is 0, okay, then I'm the one who's receiving everything. Okay? And I'm going to receive a message from processors 1 through P minus, number of processors minus 1. Okay, so that for statement is just looping through. And I'm going to issue a command. In this case, a simple command is called MPI receive. And I just put it, there's other parameters, but basically I issue a receive command saying messages are being sent to me. And I'll get the answer will be in the value part. And I have to tell it for a receive like, okay, I'm waiting for a message from this processor. So that says I have to tell it which processor I want it from. And MPI has a whole lot of variations of this and so on. MPI has almost 200 commands in it. By the way, it's huge. Fortunately, you only need about a dozen. Okay, so it turns out like you're always going to need send, receive, and a couple others. So even though MPI is a very big, complex system, you can actually get through with not that many commands, at least for your initial programming. Okay, and then I have the sum, the sum plus value, so I'm just summing them up. Now, the same program again is running everywhere, and if I'm not 0, I'm one of the others, 1 through P minus 1, in that case, the only thing I'm doing is sending. Okay, so I would then issue a send command saying, okay, send my value, and in this case, the destination is 0. So, and by the way, you better make it that for every receive, there better be a send. Okay, this is a really good way to screw up. Okay, suppose, for example, suppose I went from sources, instead of stopping at sources less than the number of processors, suppose I started at equal the number of processors. Then processor 0 would have been sitting there hung because it's waiting for a message that never got sent. Okay, that gets hard to debug. Okay, because it's often trying to figure out, like, this processor isn't going. It's like, why isn't it going any further? Sometimes you don't even know which one isn't going any further. And then the question is, well, wait, is this one not going any further because it's doing something wrong or some other processor is doing something wrong? Okay, that gets complicated to debug. Okay, now, excuse me. Now let's look at shared memory programming. You could run MPI on a shared memory system. And in fact, the interesting thing is MPI will run a little bit faster on a shared memory system than it runs on a distributed memory system, even though MPI is for distributed memory. The only reason being, in a shared memory system, you don't really send messages to the processors because you're not sending the processors, you're putting it out in memory. So it turns out when I say I'm sending a message to another processor, the shared memory system, it knows all that means is I'm just copying it from here to there for that other processor to read. So it turns out actually the overhead's a little bit less for shared memory systems. So for the shared memory system, what you typically use is a thing called OpenMP. And again, it's available on all shared memory systems. Okay, again, it's in, if you look at your standard compilers, GCC and so on, it's already in there. But it's not available on distributed memory systems. It is designed explicitly for shared memory systems. And it's compatible with C, C++, or Fortran. If you notice C, C++, or Fortran out, for some of you, Fortran is what you'd always care about and not the C, C++. For others, it goes the opposite way, depending on what discipline you're on and so on. All of these things go both ways, because they're used to calculate. Different communities use one language or the other. And what you do with OpenMP is you don't include, typically, you don't use subroutine calls so much. You end up using compiler directives. Okay? And the thing is, well, if you're not on a parallel system or you happen to be on one of the rare compilers that doesn't know OpenMP, it just ignores the directives. It just runs it like a serial code. And also, the primary use of OpenMP, which I'll show you in just a minute, is to do loops. Because remember, if you remember that picture about the parallelization and where is the time, again, the time is in loops or loops within loops and so on. So that's what OpenMP concentrates on, because that's where the time is. So here is, again, a really simple example. Here, suppose I just have 3 arrays. Okay, I'm writing in Fortran here, I guess. Okay, so I have 3 arrays, okay, and I want to say, okay, I've got a B array, a C array, and I want to say the A array is just the sum of the corresponding entries in B and C. If you're a Fortran programmer, you could say, wait, I could just write that as one line, but let's say you don't know about that I can do that in Fortran. But anyways, so I'm just going through a loop. Now I put the OpenMP compiler directives around it, the OMP parallel do, the OMP end parallel do. So it's just telling it, do this loop in parallel. So what it's going to do is, let's say n is 100, and let's say I've got 5 processors. It's going to say, okay, I have to do from 1 to 100. I've got 5 processors, or say 5 cores. I'm going to assign core 1 to do 1 to 20. Core 2 is going to do 21 to 40, and so on. So OpenMP will evenly divide that work, those iterations. It's going to assume that each iteration takes the same time. There's ways of adjusting this if you want some more sophisticated stuff. But in the simplest version, it would just assume that each one takes the same amount of time and just divides them evenly. Okay, and just assigns the cores to do their different part. Okay? You do nothing. All you did was just put those 2 commands around it, and bang, that's parallel. Okay, so the thing is, for modest parallelization, this is the easiest system to use. It's easier to use shared memory than distributed memory. Because notice, like maybe if I have loops and loops, maybe the first loop I can at least figure out how to parallelize it, then I can do something easy like this. Then I just put the directive around it. Bang, it's parallel. Maybe later stuff I haven't gotten to be parallel yet. You'll just run it in serial. Okay, but at least it'll work, right? I can just put, now, suppose instead that had been on a distributed memory system. Well, in a distributed memory system, then I had to do something like say, okay, I'm going to put part of A, B, and C on this computer over here. Another part of A, B, and C is going to go on this computer. Another part of A, B, and C is going to be on this computer. So then I can easily do that loop. Each computer can do its loop on its things. But then the part I couldn't parallelize, but then it turns out, well, wait, but now no processor's got all the data. No processor can directly use those whole arrays. So it's easier to incrementally build up parallelization on a shared memory system. Now, then you may ask, well, why isn't every big parallel computer shared memory? Okay. And the answer is because it costs more. Okay. Because that's an important consideration, actually, when you ask why in the world are these things there. It turns out, well, the things that people know how to do are build basically boards of computers and so on. They know how to link them together with the Ethernet and InfiniBand. Making a giant shared memory system is actually much more complex. It's much more expensive. So for little systems like single boards, you can get shared memory. If you're going to go large, you have to realize that all large computers, not all, but almost all, like Flux and so on, are actually distributed memory systems. So you kind of get stuck there. And so you may be able to, again, like parallelize on Flux. You could go up to 12-way on using OpenMP, but then to go bigger, you're going to have to go to MPI. So there's not much you can do about that. Now, there's another thing. This is not just for shared memory, it's for distributed memory too. Suppose I took that simple little loop and say I just change it to, instead of A of I is B of I plus C of I, suppose I say A of I is A of I minus 1 times B of I plus C of I. That destroys parallelization. Because I introduce a thing called a dependency. See, the trouble is I can't compute A of 10 until I know A of 9. I can't compute A of 9 until I know A of 8. So the trouble is I cannot break that up and say, okay, you work on A of 11 through A of 20, because it can't start A of 11 until it got A of 10 from the processor beforehand. So the trouble is, just because you have a loop doesn't mean it can parallelize, and sometimes something that looks trivial like that, all you need is one statement anywhere in the loop. Maybe the loop's doing a whole bunch of stuff. You get one statement in the loop like that, and then it blocks out parallelization. Okay. This would be an example where, I've got to come up with a different way of doing it. Okay. Because in fact, that's part of Amdahl's F. Right. That's the part that says I don't know how to parallelize it. And so you really, if that's inside your loops, that's really, really causes problems. So sometimes it's you look at it, and it's only when you look at it in detail do you start realizing some of the situations that are causing problems. Now, I talked about mainstream computing. I'll just mention a little bit about GPUs. GPUs are graphics processors. Again, they're in your laptops and so on. They have many cores in them. Okay, so your Core Duo laptop has 2 cores, but the GPU in it, I'm not sure which ones they use, like in the Apples, but say you might have 100 cores in it and it's designed to do the graphics. It does all sorts of things like shading and so on. So there's more parallelization there. And so if you could figure out how to use the parallelization, it actually gives you a tremendous speed up. And I can't remember if any of the posters this year, but I know in previous years there have been a couple of posters about people doing that, okay, coming up with clever ways of using the GPUs. So you may hear about that as being a fantastic solution. It is a good solution for some areas, but it's much harder to program. Okay? And furthermore, for many applications, it does not fit. Afterwards, I can explain it a little bit more to you. But basically, the trouble is, getting data in and out of the GPU becomes a major bottleneck. And so if I'm sweeping through a lot of data, it turns out the GPU just cannot do that. So the GPU gets a lot of speed, but it gets the speed by putting a lot of restrictions on what's going on. Okay, so you have to be very careful about when you read the literature, and when people say this, that maybe it's appropriate, but the odds are it's not. And furthermore, there's other technical things about, sometimes you'll hear that things are doing really well, and it turns out, well, one board with one GPU works. If I try to go to 2 boards, often you'll see the literature that it plummets. Okay, so just because people say it worked well for them does not mean it's going to work well for you. Okay, so I want to just review a little bit about things I've already said. So parallel programming is actually difficult. Okay, if it was easy, everyone would do it. Okay. So anyways, it's really difficult because you've got all the normal programming things. Presumably, if you program much, you've already learned out all sorts of different ways you can make mistakes. Parallel programming gives you more ways to make mistakes. Okay? It'll give you things, for example, deadlock. What happens, like suppose I'm in a situation that I need to exchange information, like about those car parts. I had to put them together. The blue needed information from the red needed information from the blue. Okay? Well, suppose what the blue processor did was say, read the data from the red and then send the data I've got to the red. So I want to receive red's data, and then I want to send to red. And suppose red did the same thing. It says, okay, receive the data that blue sent and also send the data to blue. And you realize, oops, I just screwed up. They're both waiting to receive, and neither one's sent. So I suddenly get deadlocked. Neither one can go on because each is waiting for the message from the other one before they go. It turns out in this case it would have been better to just say both send and then receive. It's got buffers and so on, so it turns out it can actually send it, wait in a buffer, and then I can receive it. Okay, and so I can do it that way. But it's very easy to make these mistakes where it's called deadlock. We've got the situation that neither one can move because, in fact, they're waiting for something from someone else. Another thing you can get is race conditions. This happens a lot like in shared memory systems where maybe there's a memory cell, one place of memory, and different processors are writing information there. Well, the end result could vary depending on what was the last processor that put a value in there. Okay? So maybe, in fact, there's a mistake that sometimes one of the processors puts a value in there that's not right. Okay? And so which one is in there is it's called a race condition. And let's say the trouble is, wait, it didn't work. And then you try debugging it. Well, the debugger runs it in a different order. In fact, it may be deterministic. Every time you run the debugger, you always get the right answer. Then you put it on the parallel system, and sometimes you get the wrong answer. Race conditions are very, very difficult to debug and so on. And so anyways, again, parallelism gives you these new problems that are going on. Now, if you're going to be writing parallel programs, it's really important to figure out kind of how parallel do you need it, and then aim at that. Because I already mentioned this bit about as you try to make it more and more parallel, as I'm going to use more and more processors, I have to make F smaller and smaller. Even if I'm using weak scaling, I may have to still reduce things a bit as I'm getting more and more processors. Each time I reduce F, that gets harder to do. Okay? And you're not going to write a perfectly parallel program. So in practice, what you do is you figure out how much parallelization do I need. You keep working on it. You make it a little bit more parallel, more and more parallel, until you get to where you are, where you need. And it's really kind of an important thing to understand in practice is kind of don't just do for what I need today and then tomorrow I'm going to need it more. But try to look ahead somewhat, but don't try to write something which is going to be infinitely parallelizable. That's just not going to work. Okay. And along with this, if you're just writing a small project that you don't do very much, but if you're writing a big project, which often happens with the parallel computing, people are often trying to say, this is a code I want to use in my research group, or my advisor wants to use in the research group, or something like that. So some of the parallel codes are actually designed that we want to use these for a long time. That's why we're writing an MPI and so on. It's actually worthwhile to say, all right, now I'm putting together a big project. Maybe I should actually think a little bit about software engineering. In particular, often what you're doing is you're starting with something that some graduate student wrote a while ago, and then some other graduate student or postdoc modified ... Maybe now would be a good time to actually look at it and figure out what is this code doing, try to organize it a little bit better, and so on. So actually when you're parallelizing something that already exists, it's actually a good time to actually think about it more and be a little more clever about how you're writing it and so on, and actually do some of the software engineering. And one of the things I'll point out actually is there's many projects that have actually ended up doing pretty well. For a big project, there's a lot of these things where what we've done sometimes is had an application professor, a scientist, postdoc, grad students, and so on. And like often we can do it with this one CS student working together. So this sometimes be an efficient way of solving big problems, big projects. Many big projects end up working this combination of things where it makes it you can use the CS students sometimes to actually kind of get you over some initial hurdles and so on. Now, here's some resources. Okay. Okay. First of all, you have CAC on campus, and they have like the Flex computer. Okay. Now, if you've gone to Ken Powell's discussion, I assume he talked some about the fact that they charge for it. It's not free. Okay. Well, there is a free system, the XSED system, which is an NSF system. Okay. It is free. Furthermore, if you need a modest amount of parallelization, if you're just starting out, it is very easy to get that's not tiny, a modest allocation. Okay. And like I use it for, we don't have a big shared memory system on campus. I have one at Pittsburgh, and I use that for my class, and it was a one-page application. That's it. So if you're doing a modest parallelization, actually XSED is very useful, and it's free. If you're going to do a massive amount of time, you're going to have to write a longer application, but presumably if you're going to use a massive amount of time, you've also got a grant proposal or something like that, and you just cut and paste from the grant proposal. I was once on a committee for NCAR, one of the NSF Centers for Atmospheric Research. We once actually allocated $2 million of computer time to a grad student. She wrote a 5-page thing justifying it, and we were just like, yep, you're right, you need it. Bang. Yeah? Did you have a question, or you just stretch it? Okay, now, you can also get computer time if you have a NASA or DOE grant or AFOSR, general DOD grants. You can get time from them, and sometimes people don't realize that this pretty much, if you've got something that needs a lot of computing and you're one of those agencies, actually they want you to use their machines. You may just have to ask your program director. It's not that complicated. And as I mentioned, things like MPI is free and so on. And if you go to my webpage there at Parlinks, I actually maintain a list of links to some of these things. I kind of try to do a best in breed, so like I don't list every possible way you could get a tutorial on OpenMP. I try to find a good tutorial on OpenMP, just one or two of them there, and so on. So I try to keep a best in breed there to make it kind of reasonable to look through. Or you can just Google, those things. And again, feel free to contact me. I'm easy to reach, and with a name like Quentin Stout, I can't really hide very well. Anyway, so I'm just Q Stout here at UMich, and again, just feel free to contact me. Feel free to ask questions. Now, here's some other resources, also, that in general, not just if you're going to do parallel computing. There's a handout actually out on the table, wherever all the handouts are, which lists this information. Right. The second one down, EECS 587, parallel computing. So actually it takes more than 75 minutes to learn parallel computing. Okay, so I actually teach a year-long, not year-long, sorry, it seems like that, half-year, one semester-long course in parallel computing. And the reason I'm mentioning it here is it's not just for CS majors. About half the students come from other departments. Okay? And so I do not assume that you know about parallel computing. I assume you're a reasonable programmer, again, in either Fortran or C++. And one of the reasons they take it sometimes is that the term project is half the grade. Okay? And they can pick the term project, I have to agree to it, but the term projects can be in their area. So there's several theses that have, and research papers and so on, that have been things that people did in the class. In fact, next week I'm on a thesis committee for defense, someone in mechanical engineering, and she did, her thesis is something she started in that class. She could do work for her research that was relevant. Now, some of the students at either the undergraduate or graduate level, we've been finding come in and actually only had like programming 1, okay? And they forgot it already. And so we also have a class that's, I hope it's going to be very useful for students, called 402, Computer Programming for Scientists and Engineers. Again, that course is designed to get people so they're competent programmers in they know what Linux is, they know how to do a variety of things. It's not a computer science course, it's specifically for people that are not in computer science. And then there's also a bunch of data-oriented classes on databases and so on. There's also things on machine learning. And so if you're in data-intensive computing, you may actually need a parallel computer to do a lot of this, but again, you're probably going to need, again, like machine learning classes and so on are quite different than, say, partial differential equations and so on. So none of the stuff I talked about here would be for learning systems, but again, some of the people in one of the term projects this semester in 587, one of the students is doing a learning algorithm. So I guess that's it. Are there any questions?
The session, so I'm going to ask you to use the mic.
I have a couple questions actually, but the first one would be, is EX280, which 402 would be the post to EX280, or would the other
Mario's.
parallel?
We have the chairman up there. I would think if you've had programming 1, you can go to 402.
Okay, so after taking 280, then 402 would be the next one to
Yes.
go to. Okay,
If you're not in computer science.
right.
Right. I mean, if you're in computer science, you've got to take
Right.
other things. But if you know 280, then 402 is the appropriate thing.
Okay, and then my other question was, I might be misunderstanding how you were doing the automotive simulation, but if you're doing it in parallel with the 3 segments, if you have a frontal crash and you have to propagate through your triangulation, how are you're sending and receiving from the red and blue, but the red would need the information of what happened through the simulation of the blue, no?
Yeah, no, right. I mean, but it needs, okay, that's actually a good question. So in crash simulation, same thing happens if you're doing fluid dynamics, a whole bunch of things. So at any given instant, for little time step, I said, I only need the things that are just adjacent to me, even though globally something's happening. Okay, but I have to pick that time step sufficiently small. Okay, there's a thing called the Courant condition. Basically, if you imagine, like I've got a pipe, okay, if I hit it with a hammer, bang, okay, the shock wave is going to go down, but it's going to go down across it at the speed of sound in metal. So if I've divided that up, I want to make sure that so I've got a little piece here in that pipe, I've got to make sure that this piece is, or that the time step is sufficiently small so that shock doesn't like in one time step go from here to here, and I kind of completely miss it in the simulation. So what I do is I make the time step small enough that, okay, if this piece here had the shock wave in it, the sound wave in it, that sound wave can at most get to the thing next to it. And so it propagates the right energy and information. Is that the...
Yeah, so then you would be, your second and third processor would have to wait until that
Yes.
shockwave got
Right.
there. Okay.
Yeah, right. That's
okay.
why I make these little time steps. And so, yeah, it propagates through.
Okay. And my other question was if you could maybe elaborate more on the differences between the core programming and parallel programming and threading, and if I was going to give Python.
Okay, first of all, I interchangeably use cores and processors
Right.
to be the same thing. So core programming is just parallel programming and so on. Threading is just a lower level technique. You're using the underlying operating system, say Linux typically, to do it, okay? And what I'm emphasizing much more is a higher level thing. Threading is actually harder to do for most people. Using MPI or OpenMP ends up often being an easier system to use, but you're doing the same thing. If you were trying to parallelize a problem, you'd have to use threads to do the same thing that you might do with OpenMP and so on. It's easier to actually debug if you're using the higher level languages. If you're using threading, you can get...
Right, and for Python, it has the global
right,
interlock.
Okay, right.
I guess that's why I was wondering
Okay,
about
right.
that.
Yeah, no, Python, different systems have it, and MPI and OpenMP don't work with Python yet.
Okay, thank you.
Yeah.
Yeah, I just with the OpenMP, when you use that, if you're using it in C or Fortran, and for instance, you showed an example of how you can't parallelize it if you make dependencies on previous or past loops. Then what is how does the compiler know? Does it?
Doesn't know, no.
So if you say I want you to parallelize this and it can't be parallelized,
It's just going to do it. It's just going to say, okay, you told me to give you, okay, you've got these iterations. It's just going to allocate them. And
Okay.
furthermore, there's things that even humans have a hard time, like what happens if I call subroutines and the subroutines, okay, you cascade it. There are parallelizing compilers, and there are analysis tools which will check that for you. Okay, but if you just tell it, paralyze it, it'll just do it. And you can, there's many ways to screw up. That's one way. You can screw up an MPI, you can screw up, and so on. Any other questions? All right, I guess that's it. Thanks for coming.
Thank you.